That's why I also gave you the percentage for the class at this point, so you know more or less where you're standing at. I will. I guess I will answer questions from the test on Monday. I will post the solution. Well, I guess I can. I guess I can. I'll put them on the companion, the solutions for the test. The reason why I'm waiting until Monday is because I still have an online student that needs to take the exam, so I don't necessarily want to give him all the answers at this point. Okay. So, I guess any questions? Well, as I said, unfortunately, I can't really talk about the exam right now. But if you want after class to ask me particular things, we can discuss it. If you are curious, I do have the key with me, but I only have one. I didn't figure I'm going to make 40 copies. Actually, I didn't even have the time to do it. I barely had the time to copy the homework. So, okay. If you notice on the homework, if you look at the schedule of classes, one thing I should point out is that the homework is up to homework 12. That will basically put us right before Thanksgiving, where the third exam is going to be. So the third exam is going to be the Wednesday before Thanksgiving, and there's a reason why I'm doing that. First of all, I learned a long time ago from past experiences that the Thanksgiving break is kind of like this magic eraser. So, I want to make sure that I get in the test before Thanksgiving, and the reason why I'm doing it the week before is, there's a couple of issues. First of all, last year when I did this, I basically didn't have a Thanksgiving because I had 150 exams to grade during the break, which was a lot of fun. But moreover, it's the nature of the material we're covering. I want to make sure that I don't put too much stuff on the third test to make it even harder. We're going to start chapter 4 today, and bless you. And the last section of chapter 4 is section 4.7. It's called antiderivatives, and I never quite completely understood why Stuart always does this, but section 4.7 has nothing to do with chapter 4. It actually is the first preamble of integrals, which is the exact opposite of derivatives. So I never really understood why he puts it in that particular chapter, but nonetheless, that's basically the last section of the chapter. And before we start talking about antiderivatives, I want to make sure that everybody remembers how to take derivatives and so forth. And so the exam is going to be basically up to that section, so I want to give you the exam before we start talking about antiderivatives. And I just... again, from past experiences, I noticed students, there's this issue that you might actually apply the wrong thing at the wrong time. Okay, so that's basically that. And the other thing I should point out is that if you actually read the syllabus, and if you actually remember what the syllabus says, we said we're going to have 12 homework sets, out of which we're dropping the 2 lowest scores. Now, if you... Okay, based on your reaction, I'm guessing you didn't remember that?
When do you drop them?
At the end of the semester. Well, how else would I know which ones are the 2 lowest?
At this point, you drop something.
No, what I'm trying to say is that this particular sheet that you're looking at right now, notice that there's 12 homework sets in it, and it only goes up to Thanksgiving, which means we're going to have an extra homework set. And I did this on purpose. I didn't tell you on the beginning of the semester, but I guess it wouldn't have mattered since you don't remember anyway. And so basically we're going to have 13 sets of homework, which means you have a potential to actually score some, extra points at the end of it. So I'm still going to drop the two lowest, but that basically means that you actually could potentially score an extra 15 points at the end of the semester. And again, I didn't say it because I didn't want to...
Get us excited?
No, I didn't want you to actually fall back on the idea that you don't have to do things because, like technically you could, not do 3 homework sets and still not lose points, and some people take that attitude, so I just don't want to, Okay, so any other thoughts?
Okay, so the whole last 3 weeks in December before we go on vacation for 2 weeks, like, are we just going to be going over what's going to be on final exams? There's not really any assignments.
There will be assignments, that's what I just said.
There was a 13th assignment after Thanksgiving break, but that's not going to take us 2 weeks.
It's not going to take you 2 weeks?
Oh, it is going to take us 2 weeks?
Well, one of the things, I don't know if I actually told you this or not, or if you actually found that out on your own or whatever, but I actually graduated last year, so I'm not actually too far off from being a student myself. And even though I guess I wasn't really taking courses the last couple of years or so, but nonetheless, the point is, I knew how much everybody really loves when they have assignments over breaks. So as a consequence, I'm not going to give you, like for instance, homework's due every Wednesday, right? So if you take out your syllabus and look at your schedule, technically there would be a homework that I could collect on Wednesday after Thanksgiving. But that would basically mean that you would actually have to work on the homework over the break. And I know how everybody really likes and enjoys that. And so as a consequence, that homework is going to be pushed probably until Friday or Monday. I haven't actually thought about exactly what I want to do. But the point is, we're going to still be covering almost the entire chapter 5 after the spring break. Thanksgiving break. Okay? So, if you again look at the syllabus, the way it's set up is we have 2 weeks of school after Thanksgiving break. And we're going to spend a good amount of time talking about Chapter 5 in the first week. And I set up, I think, the last 2 class periods for final review. Yeah, I set up the last 2 days for finals review. So, anyway, that being said, I should point out, I actually haven't looked at the e-companion today or yesterday for that matter, but this grade that you have right now is up through the first 7 homework sets. So I think I actually returned the 8th one on Wednesday. But I didn't actually update that. It's not necessarily a 2-minute job to update the grades at all points. So technically, this grade doesn't reflect your last homework. But I wouldn't assume that one homework set is really gonna alter your exam drastically. Okay, so. For the next couple of weeks, we're going to learn how to graph functions. Okay? Now, before we actually do that, there's going to be a little bit of other technical issues that we have to cover. So, let's start talking about some ground ideas first. So. The first thought we're going to look at is going to be maximum and minimum values, and I'm assuming everybody knows what a maximum is and what a minimum is, but we're going to have actually like rigorous definitions about them. So, for instance, for the next few sections or so, we're going to be dealing with different types of maximums and minimums. And there's two general types of maximums and minimums. One of them is called an absolute maximum, and the other one is called a relative maximum or a local maximum. And if you say relative maximum, it doesn't necessarily mean it doesn't necessarily give out what we're actually talking about. But if I say local maximum, then I would assume that you would understand more what's going on. As in, locally, if you look on a graph, that's going to be, you're going to be looking at a maximum, but it's not necessarily the highest of them. So let me just write out the definition. I'll look at a couple of examples, and you can tell me what you think about things. So, definition. A function f has an absolute maximum also known as global maximum at a point C if f of C is bigger than or equal to f of x for all x in capital D, where D is the domain. Bless you. The number f of C is called the maximum value of f on capital D. I probably should have wrote this differently, just because I don't want to rewrite this whole thing. Your definition in the book, I'm basically writing exactly what your definition in the book is saying, but I probably should have used my my own, in the sense that there's the exact definition with a minimum, absolute minimum. So I probably could have just wrote absolute minimum in parentheses were appropriate, so I don't have to repeat everything else. But anyway, I guess the ship has sailed. A function f has an absolute minimum at C if f of C is less than or equal to f of x for all x's in D, where D is the domain of f. F of C is called the minimum value of f on capital D. So this is the definition of an absolute maximum. This is the definition of an absolute minimum. Should I give you the definition of the local maximums and minimums first, or should we look at an example of an absolute maximum or an absolute minimum? Let me give you the other definition as well first. So definition: a function f has a local or relative minimum or local maximum at C if f of C is bigger than or equal to f of x, or f of c is less than or equal to f of x when x is near c. This is what I was saying about the previous definition. I combined the two of them together. Is this making sense? Yes.
That less than sign or greater than sign. Is that less than or equals?
This one?
Yeah.
This is greater than or equal.
Greater.
The idea is that's a good point. I wrote them the wrong way. Let's see. So minimum less than or equal, maximum bigger than or equal. I rigged it on correctly now. Is this making sense? Do you understand what I said about combining the two of them? It's a local maximum if this holds, right? The parenthesis, and it's a local minimum if that holds. Yeah? Okay. What is that actually meaning graphically? So let's see. If I have this function, so now let's say I'll name this point A, this point B, this point C, this point D, E, F, G, H. Okay, I probably could have done with less. Okay. Can you tell me what A is? Or do you recognize what am I trying to say here? I'm trying to figure out, do we have... Okay, if I can write that would be good. Absolute maximum, absolute minimum, local max, local min. So, do we have an absolute maximum? No? That keeps going, which means if you come over here, C is the largest here, but it's not going to be the largest of all. However, C is a local maximum. Is that making sense? Locally means if I only restrict myself to this little piece, then C is going to be a maximum. Similarly, if you restrict yourself here, A is a local maximum. If you restrict yourself here, E is a local maximum. If you restrict yourself here, G is a local maximum. Is that making sense? So we'll be looking at, I guess I should write them in alphabetical order, A, C, E, and G. How about absolute minimum? D is an absolute minimum. Everybody sees that? How about local minimum? B, D, F, H. Any absolute is going to be a local, right? Because the local just says locally that happens. Well, if it happens everywhere, clearly it's going to happen locally, right? Is that making sense? Okay. Now, can you give me an example of a function that would have no maximums or minimums of any kind?
Y equals 1.
Y equals 1? Technically, y equals 1 has a graph that looks like this. Right? It's a maximum and a minimum.
What?
The definition allows for equality. Is that making sense?
So for the absolute...
Is everybody seeing this? As it turns out, every point on the x-axis is going to be a local minimum, absolute minimum, local maximum, absolute maximum, which is a very boring function, but nonetheless. Do you understand this? Again, we're just looking exactly at the definition. It says less than or equal to, and so since it says less than or equal to, the equality will obviously hold here. So maxes, mins, everywhere. So let me re-ask the question. Can you come up with a function that has no maximums and no minimums whatsoever? Y equals x is an excellent function. Is everybody seeing this? X cubed, x to the fifth, and so forth. Right? Yeah?
There's no...
Well, can you find a value that actually will be larger than any other value? It keeps growing infinitely, right? Yeah, so no max min. No, growing infinitely doesn't necessarily mean much, because if I look at a function that looks like this, it'll still grow infinitely, but it'll have local minimum and maximum. Is that making sense? But there's no absolute minimums or maximums.
And do you always think you don't know what your range?
Yeah, if it's limited to a particular range, then well, the extreme value theorem and I stopped mid-sentence because I figured if I write this theorem, I can finish up the statement. If you are given a range, and the range is a closed interval, then your function will have an absolute maximum and an absolute minimum, regardless of what the function is. As long as, well, okay, let me rephrase that. As long as the function is continuous, that will be satisfied. And so, if f is continuous on a closed, and the key idea is closed interval, AB, then f attains an absolute max and absolute min in the interval AB. Okay? Two things you have to recognize here. Function's continuous and the interval is closed. Those are the two main things that have to happen for you to be able to talk about this. Do you understand why this is the case? Let's look at an example. This is A, this is B. I'll randomly pick f of A to be there, f of B to be there, whatever they are. My function is continuous, which means obviously f of A exists and f of B exists. Okay? My function is continuous, which means I gotta go from the first dot to the next dot without actually lifting my pen off the paper, right? So whatever I'm gonna do, I will be able to find a maximum and a minimum in that interval. Right? Is that making sense? For this particular picture, your max and minimum are going to be here and there, right? Because that's the way I drew it. However, your function could be doing that. At which point your minimum is actually f of A, your maximum is actually f of b. Is everybody seeing this?
That's just a closed interval, because we got what those be like function points.
Sorry?
If the interval isn't closed, would those be function points?
If the interval is not closed, right, so clearly if f is not continuous, so let me just give you some examples about things. I just said that the two conditions have to satisfy. If f is not continuous, then clearly you can start from here, go there, but if it's not continuous, you can have some sort of a vertical asymptote, at which point your function is not going to have a minimum or a maximum. Does that make any sense? What happens if the interval is not closed? Well, if it's not closed, you could technically start at a fixed point, but if this is b, my function could actually be continuous, but b actually be a vertical asymptote. At which point you have a minimum, but you're not going to have a maximum. Is that making sense? And so that's why both of these conditions have to be satisfied for you to be able to talk about the extreme value theorem. Okay? All right. Should we do a couple of problems first? Yeah, I guess we should, because otherwise, no. Let's see. Okay, so as far as your homework is concerned, the first problem that you have is problem number 6, and I don't know if I really need to, if I want to necessarily spend the time to talk about it too much. You have one of these graphs that I kind of drew before, and you're supposed to identify absolute and local minimum and maximums. So, you know, your problem's going to look similar to kind of like one of these that I just drew. So from here you have to identify which one's the maximum, minimum, and so forth. Since you all picked up on it when I did it, I assume that I don't have to spend the time talking about this anymore. Right? Okay. So, that being said, let's develop a little bit of a theory before we actually talk a little more about things. Fermat's theorem says the following. If f has a local maximum or minimum at the point C, then and if f prime of C exists, then f prime of C is equal to 0. Is this making any sense? I could give you the actual proof if you wish, but I think it's better to just talk about graphically. Okay? Think about, you have this function. Okay? A maximum will happen right here. What is the slope of the tangent line? The tangent line is horizontal, which means the derivative will be 0. Everybody sees this? Similarly, you look at the minimum here. Your tangent will be again horizontal, which means the slope will be 0. Is that making sense? However, what this does not say, and maybe I should just write that in. Okay, let's do red instead of orange. The converse is not true. which means if f prime of c is equal to 0, this is not does not mean that c is a min or a max. Okay? Example. F of x equals x cubed. F prime of x is equal to 3x squared. Clearly, f prime of 0 is equal to 0, right? However, graphically, your function looks like this. Okay? Next week we're going to find out that this particular type of point is called an inflection point. But we have a little way until we get there. Is this making sense? Yeah? Okay. So, definition. A critical number of a function f is a number c in the domain of f such that either f prime of c is equal to 0 or f prime of c does not exist. Okay. The key point here is, and maybe I should underline this, is that C is in the domain of F. Okay? So, let's look at some problems. 23 on page 204. We have f of x equals 5x squared plus 4x. We're supposed to find the critical points for the critical numbers for the function. Okay? So how do we go about finding the critical numbers? We read what it says. It says a critical number is a number in the domain such that either f prime of that number is equal to 0 or f prime does not exist. Right? So first of all, what is the domain of f? All real numbers, since we're looking at a polynomial, right? What is f prime of x? 10x plus 4. What is the domain of f prime? All real numbers. Why am I asking you of this? Well, that takes care of the second part, right? F prime of c does not exist. Well, because the domain is everything, clearly we're not going to be able to find a point for which the derivative doesn't exist, right? So the only other thing we have to look for is when the derivative is in fact equal to 0. So f prime of x equals 0 means 10x plus 4 is equal to 0, which gives x equals negative 2/5. So c is negative 2/5 is the only critical point we have. Is this making sense?
Yep.
You
Mm-hmm.
can't determine if that's factual. What is it?
We will be determining that this is in fact a minimum, but we're going to need another like 2 sections or so to get there. this is actually, what we're doing in this particular chapter is we're trying to get more and more concepts to be able to actually graph any function. And so this is kind of like the introductory part. We're talking about what is the minimum, what is the maximum, and so forth. The next section we're actually going to be dealing with something a little different that doesn't necessarily require the graphing, but then 4.3 is going to actually lay out the particular ideas that we can gather from our information, and we'll see exactly how the first and the second derivative will allow us to determine the shape of the graph, and that's basically where we're going to determine that this is a minimum. But we have a little to go until we get there. Okay. Should I do another polynomial, or is this pretty obvious? Okay. How about we do something a little more interesting? 29 on page 204. G of y is equal to y minus 1 divided by y squared minus y plus 1. Okay? So again, what we're actually asked to find is the critical numbers of this point, of the function. So what should we do? What is the domain of G? All real numbers? Why? The discriminant of the denominator is -3. I've said discriminant about 20 times, so I have a feeling you still don't remember what it is.
What does that mean again?
The quantity underneath the square root in the quadratic formula.
Oh yeah.
Which means that you can't factor it, which means that y squared minus y plus 1 is equal to 0. Y is 1 plus or minus the square root of 1 minus 4 divided by 2. This quantity is called a discriminant. If it's negative, that means you have two complex solutions, which means your function will never be 0. Right? Yes?
Yes.
If it's equal to 0, that means you only have one unique solution and you end up with a perfect square. Right? And if it's bigger than 0, then you just end up with two distinct solutions. Right? So because it's not equal to, because it's negative, this will tell us that your function over here will never cross the x-axis, right? Which means it's either going to be always positive or it's always going to be negative, right? The only thing that needs to be determined is if it's always positive or if it's always negative. Well, we don't really care because we just want to make sure it actually is not equal to 0, but this will always be positive because you add 1, right? So if you put in 0 for y, you'll end up with 1, which means it's always positive. Make sense? Okay. So, what next? Derive or differentiate, you mean to say?
What's the difference?
Well, derive, I just derived the quadratic formula right there. Derive means to
Figure out.
to solve something or to accomplish something, not necessarily to just take the derivative.
Oh, okay.
To derive, I guess, another way of saying it is to analyze. I just made that up. Anyway, what's G prime? We see a ratio, so we need to apply the, bless you, we need to apply the quotient rule. So we'll have y squared minus y plus 1 minus 2y minus 1 multiplied by y minus 1. Right? Notice this is the first time, by the way, that we're actually starting to see what I was trying to talk to you and I was trying to instill in you to do in the last 3 weeks or so. We need to figure out first of all, we need to figure out what the domain of this function is. But that should be pretty clear because it's just a rational function. The denominator can't be 0 because it wasn't 0 above, so it's still going to be all real numbers. But the next part is, we need to figure out when is g prime of y is equal to 0. So what do we need to do? We need to simplify. And this is why I've been saying it whenever you deal with derivatives, you want to be able to simplify them as much as possible, because we're going to end up with a lot of these situations now in which you need to be able to figure out when is it 0, and moreover, actually, you're going to have to figure out when is it negative, when is it positive, find a second derivative, and so forth. So how do we simplify this? So I have y squared minus y plus 1 minus 2y squared plus 3y minus 1 divided by y squared minus y plus 1 quantity squared. So far so good? Which becomes negative y squared plus 2y divided by y squared minus y plus 1 squared. So g prime of y is equal to 0 is equivalent to minus y squared plus 2y is equal to 0. And I saw your algebraic skills at work in your exam. So how do you solve this for y? You could use a quadratic formula, I guess. But observe that there's no constant term, right? Since there's no constant term, I can factor out minus y, and I'm left with y minus 2 is equal to 0. From which y is equal to 0, or y is equal to 2. Right? And so those would be your two critical points. Okay. How about 31? Capital F of x is equal to x to 4/5 times x minus 4 squared. So again, the same idea as before follows. What are the critical points of this function? Domain? What is the domain? All reals. Very good. Why all reals? It is not a polynomial. It's the fifth root. That is the key. The key is that this is the fifth root of x to the 4th times x minus 4 squared. Odd roots have domains everywhere. If this would have been an even number in the denominator here, then your domain would have been all positive numbers. Or I should say non-negative numbers. Is this making sense? Yeah, because square root of negative numbers don't make sense. So the fourth roots and sixth roots and everything else. Okay. All right. So what is capital F prime? And that was the question. So let me read it. What is f prime of x? 4/5 x to the negative 1/5 times x minus 4 squared plus 2 times x minus 4 times x to the 4/5. Again, notice what I keep saying. Two things. What is the domain of f prime? When is it equal to 0? Well, you can stare at it as long as you want. The answer is not going to just come out. We need to be able to simplify it. How should we simplify it? This is another one of those situations in which what I've been trying to instill in you is, whenever we're looking at something like this, let's write it with positive exponents so we kind of get a feel for what we're actually looking at. Okay? So this is equal to 4/5 times x minus 4 squared divided by the 5th root of x plus 2 times x minus 4 times the 5th root of x to the 4. You should be fairly easily able to answer what is the domain of f prime. Except 0. Why? Because we have a fraction, the denominator can't be 0. Right? So this is the first instance in which we actually found a critical point without actually solving it first. Right? X is equal to 0 is a critical point. Right? Okay, how do we simplify things? Because we need to figure out when this is equal to 0 now, right? And obviously, based on visually, you can tell that 4 is going to be a way to solve this, right? If you put in 4 for x, you have 0 in the first fraction, you have 0 in the second term, so you'll end up with a 0, right? But what can we do? And this is where I've done this a couple of times, and what happens if I want to actually get to a least common denominator? What would be the least common denominator? Five times the root. So I have 4 times x minus 4 quantity squared plus 5. Do you want this faster or slower? Okay. 10 times x minus 4 times the 5th root of x times the 5th root of x to the 4th divided by the 5th root of x. So far so good? I put it with the 2, so it's a 10 now. Oh, 5, yeah, sorry, thanks. 5. So far so good? Yes.
Okay, so the common denominator is 5
times the root.
Divide everything by 5.
5 times the root. This simplifies to 4 times x minus 4 quantity squared plus 10 times x minus 4 times x divided by 5 times the 5th root of x. Well, look at this. You have the 5th root of x to the 5th. Right? Which is just x. It's the 5th root of x to the 5th. So it's x. What's the square root of x squared?
It's hard to see. It looks like the 5th root of x times this.
This is the 5th root of x to the 5th. Yes?
Where do you get the 10?
2 times 5.
Oh,
The least common denominator is 5 times the square root. So multiply the 2 times the 5, you end up with a 10. Okay. So now this is equal to x minus 4 times the quantity 4 times x minus 4 plus 10x divided by 5/5 root of x. And so this becomes x minus 4 times 14x minus 16 divided by 5 times the 5th root of x. And if you want to set this equal to 0, you end up with x equals 4 and x equals, what is that, 8/7?
What'd you do with the 10x?
What do you mean, what did I do with it?
Like, it seems like you didn't really multiply it.
Didn't I? What did I end up with?
14 minus 16. It's like it's here.
What do you get here?
Oh, okay, I see.
Okay? Ready for the next step? Everybody sounds so enthused. If f has a local maximum or minimum, then C is a critical number of f. Is this making sense? Why? Well, if you think about before, we had Fermat's theorem that said, you know, if f has a critical, if f has a minimum or maximum, then the derivative was 0, right? Or actually, and the derivative existed, and the derivative was 0, right? So this is basically exactly pretty much the same idea, only in a more general term. So this should give us a little bit of an indication of how to figure out when something is a maximum or a minimum. And this is the called the closed interval method. To find the absolute maximum and minimum values of a continuous function on a closed interval AB. In your book it has 3 steps. I don't necessarily want to write all of them that much. Remember, the extreme value theorem says if I have my functions continuous on a closed interval, it will have an absolute maximum and it will have an absolute minimum, right? So step number 1 says the following: find all critical points of f, say C1, C2, up to Cn. Step 2, the smallest of f of C1, f of C2, up to f of Cn, f of A and f of B is the absolute minimum, and the largest is the absolute maximum. Is this making sense? Since my function is continuous, is defined on that interval, all of these f's will make sense. So the only thing I have to do is I have to figure out which one is the largest, which one is the smallest. So I just find all possible critical points and just plug in values and see which one is the largest, which one is the smallest. Is this making sense? Okay. So, let's see, I guess we have 15 minutes. Do you want me to do a polynomial or should I do something a little more interesting?
Do we have something a little more interesting on the board?
Of course you do.
Well, crap, let's do that.
Sure. Let me pick one that's not hard. So let's look at 37 on page 204. We have f of x equals 3x squared minus 12x plus 5, and the interval I'm looking for is 0 and 3. So how do we find critical points? Well, notice that I'm looking at a polynomial. Its domain is going to be everything. The derivative's domain is going to be everything. So I'm not going to find a critical point there, right? So I need to just find the derivative and find when the derivative is 0. So f prime of x is 6x minus 12, which means x is equal to 2 is a critical point. Is that making sense? And now the only thing I have to compute is f of 0, f of 2, and f of 3. Right? This is what I was saying earlier, right? If you look at what I was saying, you find all the critical points. We did. And now you compute all the f's plus the f's at the endpoints. And you just pick whichever one's larger and whichever one's smaller. Okay? So f of 0 is 5, f of 2 is negative 7, and f of 3 minus 4. Because you get 27 minus 36 is negative 9 plus 5 is negative 4. So maximum, minimum. Is that making sense? Yes. Yes, I'm looking for f, not f prime, right?
Why do we use 0, not 1?
Your domain, your interval is between 0 and 3. So your endpoints are 0 and 3, and the critical point is 2. Right? This is going to be the critical point. These two are the endpoints.
Oh, I was all the points.
No. Well, you can't do all the points because you're looking at an interval. It's an infinite number of points. Is this making sense? Okay. Let's see. Which one would you like to see? 43 is a square root. 45 is a trigonometric. 47 is an exponential. Which one? Exponential? Okay. 47. We have f of x equals x e to the minus x squared over 8. And the interval we're looking for is between minus 1 and 4. So what should we determine first? Clearly, your function is going to be continuous everywhere, right? Between minus 1 and 4. Otherwise, we couldn't really be applying the closed interval method, right? So, and besides, you can observe that anyway, right? Exponentials are defined everywhere. Making it squared doesn't really change anything. Multiplying I by x, again, doesn't change anything, right? So what is f prime of x then? E to the minus x squared over 8 plus x e to the minus x squared over 8 times minus x over 4, you say? Or minus 2x over 8? If so, you wish to? Yes? Okay. Well, again, just by looking at it, the domain will be all real numbers, so clearly minus 1 and 4 will be in it, right? And it's continuous on that interval. So there's not going to be any critical points from that perspective, right? So the only other perspective to look at is, when is this actually equal to 0? Right? Okay. So f prime of x is equal to 0 means e to the minus x squared over 8 plus x times e to the minus x squared over 8 times minus x over 4 is equal to 0. How do we solve something like this? First thing, observe that both terms involve an exponential. How about if we factor it? What are we left off with? From the first equation, expression, we're left with 1. From the second expression, we're left with minus x squared over 4. Has to equal 0. Right? Is that making sense? Okay. Next step. The exponential. What is so nice about exponential functions? They can never be 0, nor they can be negative. Right? This means that the only way I can get 0 is if 1 minus x squared over 4 is equal to 0. Right? So far so good?
Oh, wait.
Yes.
You said the exponent can't be equal to 0.
That's what I said.
Okay. Why is that again? Oh yeah, because e to the 0 would just be 1.
That's not why. Think about the graph of... You're taking a positive number, raise it to whatever power you want. How are you going to make it 0? Or think about your graph. What is the graph of e to the x?
So exponential. Okay.
Okay? Alright, so how do we solve 1 minus x squared over 4 equals 0? I have x squared over 4 is equal to 1, which means x squared is equal to 4, which means x is equal to plus or minus 2. Right? So these are my critical points, right? What do I need to evaluate my function at? Negative 1, 2, and 4. Is everybody understanding why not negative 2? It's not in the domain. It's not in your interval, right? The interval we're looking for is between minus 1 and 4. Negative 2 is not in that interval, right? So evaluating f at negative 2 doesn't really help me at all. Okay? So now all I have to do is just evaluate it. F of negative 1 will be minus e to minus 1/8. F of 2 will be 2e to minus 1/2. And f of 4 is just 4e to minus 2. Right? Well, obviously, f of negative 1 is the minimum. Do we need to spend any time on that? It's the only one that's negative. Right? Okay, so now which one of the remaining two is the maximum? 4? Why? But it's negative. So how about we find out? Is 2e to minus 1/2 less than 4e to minus 2. If it isn't, if I get to something that's not true, then clearly the inequality is the other way around. Right? So what are we saying? We're saying this is the same thing as, how do you want to do this? Do you want to work with negative exponents, or should you see positive exponents? First of all, notice that if I divide by 2, I'll end up with e to minus 1/2 is less than 2e to minus 2, right? This is the same thing as 1 over e to 1/2 is less than 2 over e squared, which is equivalent to saying e squared is less than 2e to 1/2. So is this true? We still don't know? Think about this. E squared less than 2 times the square root of e. No, right? Is that making sense? If you still don't see it, from here, divide both sides by e to 1/2. This will give you e to 3/2 is less than 2, which by now should be more obvious that it's false. Why is it false? E is 2.71. You're raising it to a power larger than 1, so this number has to be bigger than 2.7. I don't know how much bigger, but it's clearly bigger than 2.7, right? 2, well, it's not bigger than 2.7. Which means we come up here and we say that actually is the maximum. Yes?
Okay, so this whole thing we just did is trying to determine...
Which one of the two is maximum and which one of the two is minimum, yes.
Okay, but we're trying to figure out which one is bigger than the maximum. Okay.
Is this making sense? Wonderful. Let's see. Since you're going to have to do 48, if I look at 35 on page 204, f of x equals x ln of x. What are the critical points of f? What is the domain of f? Zero to positive infinity? Yes? And 0 cannot be part of the domain since ln of 0 doesn't exist. Right? Okay? So now what is f prime of x? Ln of x plus 1 over x times x, which is just 1, right? What is the domain of f prime? Same as before, so no critical points there, right? Next topic would be, well, when is f prime of x equal to 0? And you might be inclined to say never, but that's not correct. So ln of x plus 1 is equal to 0 is equivalent to ln of x is equal to minus 1. And so x is e to the negative 1. So c is just 1 over e. I'll just write it as 1 over e. Is that making sense? Okay. I guess we'll stop here then.
Oh, wait, we're not, figure out the maximum value?
No, this was just to find the critical points.
Oh, okay.
We weren't given an interval.
Oh, okay.